Defeasible logic and non-monotonic logic are families of logical systems designed to model forms of reasoning in which conclusions may be withdrawn in the light of new information. In contrast to classical logic, where valid conclusions are permanent once derived, defeasible reasoning allows for conclusions that hold normally, typically, or in the absence of counter-evidence. The core idea is that not all reasoning is deductively conclusive. Much everyday, scientific, legal, and moral reasoning seem to proceed by drawing plausible conclusions that remain open to revision. Defeasible and non-monotonic logics aim to formalize this kind of reasoning while preserving logical rigor. Classical logic is monotonic. If a conclusion follows from a set of premises, then it still follows after adding further premises. However, human reasoning often violates monotonicity. New information can undermine earlier conclusions without introducing inconsistency. For example, learning that an animal is a bird may justify the conclusion that it flies, but learning that it is a penguin defeats that inference. Classical logic can represent such information, but it cannot explain why some inferences should be treated as provisional rather than strictly valid. Defeasible logic was introduced to bridge this gap between formal logic and common-sense reasoning. The most important difference between defeasible or non-monotonic logic and classical logic lies in how inference behaves under the addition of information. In classical logic, adding premises can only increase what is derivable. In defeasible logic, adding premises can block or defeat previously acceptable conclusions. Another difference concerns conditionals. Classical logic does not distinguish between strict rules and defeasible generalizations. Defeasible logic often introduces a special defeasible conditional, read as normally, if A then B, or A implies B by default. Classical validity is all or nothing. An argument is valid if and only if. In every model in which the premises are true, the conclusion is also true. Defeasible validity is, in at least one sense, weaker. A defeasibly valid argument supports its conclusion in normal circumstances, but this support may disappear when additional information is introduced. Roughly speaking, we can say that an argument is defeasibly valid if, and only if, it is reasonable to expect the conclusion to be true if the premises are true. Thus, defeasible validity captures a notion closer to justified belief or reasonable inference rather than deductive certainty. It does not guarantee truth preservation in all possible situations, but only in those that are sufficiently typical or normal. Consider the following argument. Argument 1. Birds fly. Tweety is a bird, so Tweety flies. This inference is intuitively acceptable. In defeasible logic, birds fly is not interpreted as a universal and necessary principle. According to this view, birds fly expresses a defeasible generalization. Most birds fly absent special circumstances. Given no further information, concluding that Tweety flies is therefore reasonable. Since it is reasonable to expect the conclusion to be true if the premises are true, this argument is defeasibly valid, even though the truth of the premises does not guarantee the truth of the conclusion. Now consider the expanded case. Argument 2. Birds fly. Tweety is a bird. Penguins do not fly. Tweety is a penguin. If Tweety is a penguin, Tweety must be a bird. So Tweety flies. Intuitively, this argument is not valid, and defeasible logic blocks the conclusion. The more specific information that Tweety is a penguin defeats the default inference from bird to flies. Since Tweety is a penguin and penguins do not fly, it seems reasonable to conclude that it is not the case that Tweety flies in this example. Hence, it is not reasonable to expect the conclusion to be true if the premises are true in argument 2. Therefore, the argument is defeasibly invalid. The set of premises in argument 1 is a subset of the set of premises in argument 2. This illustrates how defeasible logic is non-monotonic and how adding premises to a defeasibly valid argument can make it invalid. The syntax of defeasible logics typically extends propositional or first-order logic with additional operators. Alongside classical connectives, one often finds a defeasible conditional, commonly written as A right arrow B, to be read as normally if A, then B. Some systems distinguish strict rules, classical implications, defeasible rules, default conditionals, and defeaters, rules that prevent conclusions without asserting their negation. This syntactic distinction allows the logic to represent different strengths of inference. Semantically, defeasible and non-monotonic logics are often interpreted using preference-based models, ranked worlds, or default structures. Worlds are ordered according to how normal or typical they are, given the information available. A defeasible conditional A, right arrow B, is true if and only if, in the most preferred or normal worlds where A holds, B also holds. When new information is added, the set of most preferred worlds may change, thereby defeating earlier conclusions. Other semantic frameworks include fixed-point constructions, argumentation frameworks, and stable model semantics, especially in logic programming. In these systems, ordinary classical consequence is defined as usual, truth preservation across all relevant models. Defeasible consequence is defined relative to preferred models or extensions. A conclusion defeasibly follows from a set of premises if and only if it holds in all admissible or preferred interpretations of those premises. Defeasible validity is thus context-sensitive and information-dependent. An argument may be defeasibly valid relative to one knowledge state, but not relative to another enriched state. Several proof methods have been developed for defeasible and non-monotonic logics, including rule-based proof systems distinguishing strict and defeasible inference, argumentation frameworks where arguments attack and defeat one another, tableau systems with preference constraints, and logic programming approaches, such as default logic and answer set programming. Each method highlights different aspects of defeasibility, such as conflict resolution or priority handling. Defeasible logic can be combined with other logical systems, such as modal logic, epistemic logic, and deontic logic. In deontic contexts, defeasible rules are especially useful for modeling exceptions to obligations, such as, normally, one ought not to lie unless doing so prevents serious harm. Some argue that defeasible deontic logic can be used to adequately symbolize so-called prima facie duties, such as, if you promised, you should keep your promise. Such combinations allow formal reasoning about norms, obligations, permissions, prohibitions, beliefs and actions, etc., under conditions of uncertainty and exception. Many defeasible and non-monotonic systems are sound and complete with respect to their intended semantics, though completeness results are often more delicate than in classical logic. Decidability and computational complexity vary widely. In general, richer systems offer greater expressive power at the cost of higher complexity. Defeasible and non-monotonic logics provide formal tools for reasoning that is flexible, context-sensitive, and revisable. By distinguishing strict entailment from defeasible support, they aim to illuminate how rational agents reason under uncertainty and exception. These logics do not necessarily replace classical logic, but rather complement it by modeling another important dimension of rational thought, reasoning that can adapt to new information.